Hello, everyone. Welcome back to your channel of Math Made Easy. In today's session, it's the same day, but for you, it may be a different day. I'm going to go over independence of events. Okay? It's not July 4th, I know, but nevertheless, we are going to discuss independence. Okay. So when we say independence, what do I mean? Or what do we mean? I will give you a made up example. So I will work the numbers in my head. It's no big deal. And we'll show you something interesting. So what we are doing here, we have a Venn diagram with two events, A and B, as we usually do. But now A and B, I have the probability of A, let's say it's 0.4, and the probability of B is 0.5. This is A, and that's B. And the intersection part, A and B, is 0.2, meaning this is 0.2 and 0.2, and this is 0.2 and 0.3. Let's go over the definition of conditional probability. How do I calculate the probability of A given B, the probability of A given not B, the probability of B given A, and the probability of B given not A? And maybe to complete it, the probability of not A given not B, and the probability of not B given not A. Let's do that. We know that the probability of A given B is the probability of A and B over the probability of B. Notice, before we continue, if the probability of A is 0.4, the probability of not A would be 0.6, right? And if the probability of B is 0.5, then the probability of not B is also not 0.5. Let's write all of those. So, probability of A and not B divided by the probability of not B. In fact, I should have write it as on the same line because I wasn't planning to write those here, so I don't want them to be very crowded. I'm going to write it as the probability of not A and not B divided by the probability of not B. The probability of B and A divided by the probability of A. The probability of B and not A divided by the probability of not A. And the probability of not B and not A, or not A and not B, it's the same thing, but this time it's divided by the probability of not A. Now, what is the probability of A and B? We said it's 20%, right? So it's 0.2 divided by the probability of B, which is 0.5. So I get 0.4, right? If I divide 2 over 5, I get 40%. What is the probability of A and not B? Notice this is A and B, so A and not B is also 0.2, right? Because the probability of A altogether was 0.4. This is the, so let's write, this is the probability of A and B. This is the probability of A and not B, or B and or not B and A. And this is the probability of not A and B, or B and not A. It's the same thing. So A and not B is this guy. So if this is, let's write them in numbers. We said this is 0.2. So this also is 0.2. And this is 0.3, right? If it's 0.5 altogether, so this is 0.3. So we can just write. Okay, A and not B is here, it's 0.2. Not B is 0.5, so I still get 0.4. Not A and not B. Well, we didn't write not A and not B, but this is not A and not B. What's outside of all of them? So if this is 20% and this is 20% and this is 30%, they add up to 70%. So this guy is 30%. So it's 0.3 divided by not B, which is 0.5, you get 0.6. B and A, or A and B, is 0.2 over probability of A is 0.4, so you get 0.5. B and not A, this is B and not A, it's 30%, 0.3, over not A, which is 0.6, so you get 0.5. And finally, not A and not B is 0.3, divided by not A, which is 0.6, you get 0.5. Okay. Now, what was the probability of A? It was 0.4. And what is the probability of A given that you know B occurred? It's still 0.4. So what is the probability of A if you know that B did not occur? Still 0.4. So A and B are independent of each other, right? Now, let's look at not A. What is the probability of not A is 0.6. So what is the probability of not A if you know that B did not occur? It's still 0.6. What is the probability of B? It's 0.5. But if I tell you A occurred, oh, it doesn't matter, still 0.5. Okay, so what if I tell you A did not occur? It's still 0.5. And the probability of not B is 0.5, we said. What if we already established that um, if, so here we say we didn't do the probability of, in fact, we didn't do the probability of not A given B and not B given A. So just to complete, here we say it's the probability of not A and B divided by the probability of B. And here we say it's the probability of not B and A multiplied by the probability of A. Again, probability of A and not A and B, not A and B is that, which is 30%, divided by the probability of B, which is 50%, so you get 0.6. And the probability of not B and A is this guy, which is 20%, divided by the probability of A, which is 0.4, you get 50%. Notice that originally the probability of A prime was 0.6. After we know that B occurred, it's still 0.6. Probability of not B, given that we know A occurred, is 0.5, and originally it was 0.5. So regardless of what happens to A, the probability of B doesn't change. Regardless of what happened to B, probability of A doesn't change. Regardless of what happened to not A, and so on and so forth. So you can see that that's independence. But guess what? If this guy is the same as the probability of A, and this is the same as the probability of A, and this is probability of A prime and whatever, we find out that the probability of A and B in case of independence, if and only if two or more events are independent of each other, the probability of A and B equals the probability of A times the probability of B. Instead of saying it's the probability of A given B times B, well, probability of A given B is the same as the probability of A if A doesn't depend on B. You don't have to tell me B happened or B didn't happen. I don't care. Probability of A doesn't change. And like we said earlier, that if two or more events are mutually exclusive, the or becomes plus. Now we say if and only if two or more, two events or two events are statistically, we should say statistically independent, then the and becomes times. Not always. Many students say, oh, and means times. No, you have to establish that the events are independent. And it doesn't matter if I have 10 events and all of them are mutually independent, like every two of them are independent of each other, then the probability that they all occur is the product of these, of their own probabilities. I hope this explained it. We took a whole example, and now we are going to discuss something you learn if in reliability. That was, my area of expertise, or that's where I had my like dissertation in reliability. So what are you talking here about reliability? What is reliability? If you want to make an item more reliable, you want it to stay functioning or performing its intended use under specific conditions of that you specify for a long period of time. So to give you an example, uh, reliability, if you want to make a product reliable, then we don't expect to have high performance. And why is that? I don't want to spend more time on, but just quickly, I'm going to give you the example of producing a commercial vehicle versus a race car, or commercial airplane versus a fighting jet. Do you see that my if I'm doing like, or if I'm producing a vehicle for commercial use or an airplane for commercial use, I will think about reliability over and over and over again, even if my performance is not up to par. Why? Because the human life is priceless, right? So I don't care to spend more money, make it more bulky, create what we call like spare parts or like backup systems so that my vehicle doesn't fail or I don't get, horrible accident. And because my design would be more bulky and the payload would be heavier, the car is not intended. Yeah, some of them are really fast, but if you compare these to, say, like Formula One vehicles, race cars, which one is more reliable? You see it all the time when you look at races and the cars, they lose their tire and they, have engine problems and whatever, because at this point, I don't care about reliability. I want performance. I want to increase. And you can see that in performance and reliability go like a seesaw. If you spend more time and more money to make it more reliable, it would be less. The performance would be less. Same thing for commercial flight, like if you have an airplane versus a jet, like a fighter jet. You don't care about reliability in a fighter jet. Of course you care, but what I'm saying is the performance. The performance is more important there, but the reliability is definitely more important in a commercial airplane. So let's take two examples here. Suppose I have a system, and the system is made up of, let's say, three components. Three components, and they are in series like that. And each one of them has a reliability of 90%, meaning they have 10% that either one of them uh, will fail. And we say they are independent. In real life, they are not independent. But it's more hard to make it non-independent and go into, you will do that maybe in an advanced course. But here, We assume independence to make life easy because if they are independent, I would say the probability that this system survives is that the first survive and the second survive and the third survive because they are in series, right? Oh, they are independent. And means times. So the probability of the system becomes zero point 0.9 times zero point 0.9 times zero point 0.9 equals 0.729. Horribly low. See, now I cannot produce it with a probability of failure that is roughly 27%. That's very high. So somebody will suggest to you that you do what we call an like a system at a system level redundancy. Okay. So you will say, okay, so I will take these three, even though they are in series, I would make another exactly the same system in parallel with it. Okay. And we call that high level redundancy. You'll see why in a second. So now, as long as one branch works, you're fine. In order to for this, so this system, first of all, you can say either the top branch works or the bottom branch works or both work, right? What is that called? The or. So basically the probability of the system to survive is what? You say either this works, which is 0.729, or this works, which is 0.729. But remember when we said the or, I have to subtract the probability that both work because I would be adding that twice. Anyway, it's easier when you work a problem like that to say, no, I want to know what is the probability that the system would fail and then subtract it from one. It's much easier. Why? Because in order for this system to fail, what should happen? In fact, no, in this case, the probability that the system survives is easier. Why? Because the system fails if if this and this fail, or this and that, or this and that, or this and that, or this, or two from here, or it's too many. So it's easier to say, well, I can replace the top branch by 0.729 because I already know that that's the reliability, and I replace that with 0.729 and then say, in order for this system to survive, either the top survives or the bottom survives or both survive. So it's the probability that or the probability of or, right? So that would be 0.729 probability of A plus the probability of B minus the probability of A times the probability of B. And we do this 0.729 plus 0.729. Already we exceeded 100%, so it's impossible, right? But when we say minus 0.729 square, I get roughly 92.7. Yeah, so the backup system increased my reliability from 73 to 92 and a half. Let's say 0.2927. And then another engineer would say, wait a second, I have another idea. Instead of making the whole system at a high level redundancy, no, I'm going to take this element. I picked zero point 0.9 just for simplicity for all of them. I made them all the same. But if that was 0.9 and this is 0.8 and this is 0.85, I still can get a different probability here and there, and I would add them and subtract their square, right? But this time he said, no, I want to do it like that and make a low-level redundancy. So every element is redundant. You see that? I'm still using 6 elements, but on the top case, I made the whole system. I want you to think which one is better before we do the math. Just your own idea, and then you will see if you are answering, if your answer is correct or no. Here, you should know which one is better, but here we have, if I want to find the reliability of the system, it's so complicated. If you say, what is the probability that the system survives? It's, you can have these three, or these three, or these three, or those three. It's so complicated. It's much easier to say, what is the probability that the system would fail? The system, this is, or you say it slightly different. You say, what is the probability that this system survives? What is that? It survives if this survives, or that survives, or both survive. So it's much easier to say, what is the probability that this one would fail? It only fails if both fail. This fails and that fail, right? And because they are independent, it's the probability of failure of one times the probability of failure of the other. If this one has a probability of failure of 10%, zero point 0.1, and this is zero point 0.1, so the probability that both fail is zero point 0.1 times zero point 0.1, or 0.01, which means its reliability is 0.99, right? 1 minus zero point 0.9 gives you the probability that this one fails. Square gives you the probability that these two fail. So the survival of the system would be 1 minus that, 99%. And this is 99%, and this is 99%. So the probability that the system survives is the first module survive, and the second survive, and the third survive. So it's this number to the power of 3, 97%. 97 to 2 decimal place, or even 970. So this turns out to be more reliable than that, even though here I use six terms and or six modules, and here I use 6 modules. So I made the system more robust, right? By doubling the price, but if I didn't pay attention, I may increase it from 72 to 92, while I could increase it from 73 to 92, while I was able to increase it from 73 to 97. And of course, if you add another element, then this would be 0.999, because the probability that each subsystem fails is that this fails, and this fails, and the third fail, which is 999. So that would be 997 roughly. It's almost non-failurable, or failure. There is no failure here, right? So you can see now that independence, as I said, you will never have independent, because basically think about it. If I have a system like that, and if this element fails, the load, because before they were sharing a load. If one fails, then this is sharing the whole load. Its reliability will never stay at 90%. It will drop, and these numbers will be smaller. But because we don't know how to deal with that case at this level, at least, we are going to assume independence to make life easy, and the calculations would be much, much easier. I hope independence was clear now to you. So before we were talking about conditional probability last time, it's very involved. You have to go back and review it. And now we check. What I want you to understand is that now we have 2 statements that are very important. If 2 events are mutually exclusive, the or becomes plus. If they are statistically independent, the and becomes times. And maybe one worth mentioning, mutually exclusive events can never be statistically independent. Think about it and see why. Okay? And you should see it because we did something like that. Remember when we had two events and we said probability of A says 20% and this is 30%. If I tell you B occurred, what is the probability of A? It becomes zero. If it didn't occur, then it becomes whatever, zero point 0.2 over zero point 0.7. Remember we did this example? So knowing whether B occurred or not affects the probability of A. So they cannot be independent. So independent events have to overlap, not any overlapping, but such that the joint probability is the product of both. Okay? But this is very important because many students confuse the two with each other. They think they are synonyms. No. Mutually exclusive events, meaning they don't have overlap. Independent events mean they have overlap, but a specific one. The overlapping or the intersection of these events is the product of the individual events. Okay, I hope that clears this misconception that I've seen over the years in many students. And again, if you have any questions, just drop me a comment in the comment section and I will try to get back to you as soon as I can. Thanks for watching and hope to see you soon.